On May 1st, 2024, a seemingly normal sunspot appeared on the eastern side of the Sun. At first, it looked like an ordinary sunspot, one of many that appear and disappear. But over the next few days, it grew at an incredible speed, becoming 17 times larger than Earth. Scientists named it Active Region 3664, and it quickly lived up to its name. This massive sunspot released powerful solar flares, some so strong they caused coronal mass ejections aimed directly at Earth. The result was one of the most spectacular aurora displays ever recorded. Bright, colorful lights filled the skies in places that had never seen them before. NASA stated it was the strongest geomagnetic storm in 500 years, even affecting observatories deep underground. The Sun didn't calm down after those intense solar storms in May. It continued producing bursts of M and mild X-class flares, keeping space weather experts alert. Then, on October 3rd, it released a massive X9.0 flare, the strongest in 7 years, right from the middle of its surface. Within a week, a powerful G4 geomagnetic storm struck Earth. This storm lit up skies with vibrant auroras in unexpected places and disrupted radio signals in some areas. All of these events signaled one thing: the solar maximum was approaching. NASA has now confirmed it. The Sun's magnetic field has flipped, marking the arrival of the solar maximum. But what does this mean for Earth in the coming months? How long will this period of increased solar activity last? Most importantly, will it affect global temperatures and make our planet warmer in the next year? The Sun may look like a steady ball of light, but it's far from stable. Every 11 years, it undergoes a major change known as the solar cycle. This cycle affects the Sun's activity, magnetic field, and appearance, influencing our planet in many ways. The discovery of the solar cycle dates back to the late 1700s, when astronomers noticed something unusual about sunspots, dark spots on the Sun's surface. They realized these spots didn't appear randomly. Instead, their numbers increased and decreased in a regular pattern over time. This pattern repeated every 11 years, and scientists later called it the solar cycle. After this discovery, astronomers began studying the solar cycle more closely. For years, they recorded solar activity by counting sunspots. As technology improved, they noticed two other changes during the cycle. First, they discovered that the Sun's magnetic field, which comes from its charged gas or plasma, changes completely during each cycle. The magnetic poles flip, meaning the north becomes south and the south becomes north. This pole reversal happens around the solar maximum, marking the middle of the cycle. Second, the Sun's activity, including solar winds, flares, and coronal mass ejections, reaches its peak during the solar maximum and its lowest point during the solar minimum. Because of these findings, scientists now monitor solar cycles by tracking both sunspot numbers and magnetic field changes. Since the solar cycle's discovery, astronomers have tracked each cycle and given them numbers. We're currently in solar cycle 25, and each of the 24 cycles before it had unique features. While most cycles followed the typical pattern of rising to a maximum with many sunspots and then declining into a quiet minimum, two periods in history stood out. The first unusual period was the Maunder minimum, which occurred between 1645 and 1715. During these 70 years, solar activity was extremely low, with only about 50 sunspots observed, compared to thousands in a typical cycle. This period coincided with the Little Ice Age, a time of colder-than-average temperatures. Rivers that rarely froze, like the Thames in London, froze over, and Europe faced harsh winters. The second was the Dalton minimum, from 1790 to 1830. Though less extreme, it also featured lower solar activity and cooler global temperatures. Major volcanic eruptions, like the 1815 eruption of Mount Tambora, added to the cooling, leading to the year without a summer in 1816, when crop failures and food shortages hit Europe and North America. More recently, solar cycle 24, which began in 2008, was one of the weakest in over a century. It had fewer sunspots, solar flares, and coronal mass ejections than expected. This raised questions about why solar activity varies and whether a future grand minimum, like the Maunder minimum, could happen again. When solar cycle 25 began in December 2019, scientists predicted it would be weaker than the previous cycle. However, they were wrong. By August 2024, The average daily sunspot number reached 299, more than double the expected value. This level of activity hadn't been seen in over 20 years. Interestingly, Solar Cycle 25 reached its peak earlier than scientists predicted. Initial forecasts expected the peak in July 2025 with about 115 sunspots. But by January 2024, NOAA revised its prediction, expecting the peak between January and October 2024 with 137 to 173 sunspots. On October 15th, NASA confirmed the start of the solar maximum. However, this doesn't mean we've seen the peak of activity yet. While the solar maximum has begun, determining the exact peak will take time. Now back to Mo globes. These amazing globes bring the wonder of space to your desk. Powered by light and hidden magnets, they spin quietly, requiring no cords or batteries. Mo globes come in over 40 designs, including a space-themed collection with planets, moons, and constellations. Scientists need time to identify the sun's true activity peak. This process involves tracking solar behavior over months or even years, as the peak is only confirmed once a steady decline in activity is observed. Over the past 2 years, the sun has already shown heightened activity, with frequent sunspots indicating an active phase. Experts predict that the sun will remain in its maximum phase for roughly another year before slowly transitioning to the quieter solar minimum. This makes the coming months critical, as we may witness intense geomagnetic storms and stunning auroral displays. Some of history's strongest solar storms have left significant impacts on Earth. The Carrington event of September 1st to 2nd, 1859, is the most famous. British astronomer Richard Carrington observed a massive solar flare, and within hours, a coronal mass ejection struck Earth, triggering a powerful geomagnetic storm. Telegraph systems across Europe and North America malfunctioned. Some operators reported electric shocks, while others found their equipment operated without batteries, powered by the storm's electric currents. The aurora borealis extended as far south as the Caribbean, illuminating the night sky so brightly that people could read newspapers outdoors. In the Rocky Mountains, miners awoke and started their day early, mistaking the auroral glow for sunrise. In May 1921, another significant storm, the New York Railroad Storm, disrupted Earth's electrical systems. It caused fires at a railway station in Brewster, New York, and interrupted railroad signaling across the northeastern U.S. In August 1972, a solar storm between the Apollo 16 and 17 moon missions created conditions that could have been fatal for astronauts exposed to its radiation. This event also triggered underwater mine explosions off Vietnam due to magnetic activity affecting sensors. Another major incident occurred in March 1989, when a solar storm caused a blackout in Quebec, Canada, leaving 6 million people without power for over 9 hours. This event highlighted the vulnerability of modern power grids to solar activity and led to improved protective measures. More recently, in early 2022, a solar flare caused geomagnetic storms that resulted in the loss of 40 newly launched Starlink satellites. Today's society relies heavily on technologies that depend on stable magnetic environments, such as satellites, making us more susceptible to disruptions from solar storms. The economic damages from a Carrington-class event today, a critical question arises. Does solar activity significantly increase Earth's temperature, contributing to global warming? During the solar maximum, there is a slight rise in the total solar energy reaching Earth, which can cause small climate fluctuations. However, these variations are minor and do not significantly impact global temperatures. Observations show that while solar activity has followed an 11-year cycle without a net increase in energy since the 1950s, global temperatures have risen substantially, indicating that the sun is not the primary driver of recent global warming trends. High solar activity poses risks, but also offers benefits. For instance, it shields Earth from harmful cosmic rays, reducing long-term damage to satellites. However, intense solar storms can endanger NASA's missions by exposing sensitive electronics to high-energy particles and disrupting communication. One of the most exciting aspects of the solar maximum is the possibility of auroras. When charged particles from coronal mass ejections collide with Earth's magnetic field, they create stunning light displays. Daylight auroras occur near Earth's poles when magnetic fields link, allowing particles to stream down. Nighttime auroras form when stretched magnetic fields snap, directing particles to the poles. Auroras typically appear green when particles interact with oxygen at lower altitudes, while rarer red auroras occur higher up and require greater intensity to be visible. The best places to see auroras include Canada, Alaska, Iceland, Norway, and southern regions of New Zealand and Tasmania. As we approach the solar maximum, these spectacular phenomena remind us of our connection to a dynamic universe, inspiring awe and wonder. Like the auroras, products like MOA globes offer a chance to bring the beauty of space closer to home.